So far, when we describe the behavior of our sample values, of our experimental values, we use different words for that. We used word frequency, we used word density, we used word percentage, percentile, quantile, and so on and so forth. We never used the word probability, which is quite important for statistics. Let's learn what links frequencies and probabilities. So first of all, in order to understand the difference and the similarities of these two terms, you need to think about timeline. You are located here, so this is what is now. This is past and this is future. Well, in the past, you have collected a sample and you carried out some measurements. So now you have a sample. Now all measurements are already done. And now you can describe it by computing, for example, frequencies. While in the future, you can collect a new sample. And the idea is, can we say something about this new sample that will be collected in future by knowing information about our current sample? Well, you remember that when we describe our current sample, we compute a lot of statistics, and one of the most important statistics is this frequency. So frequency, it's a property of your current sample, which you already collected in the past, and which has a fixed size n. So this is the sample size. And this is how we compute relative frequency, right? So we count all favorable observed outcomes, and we divide it to all observed outcomes. For example, what it means favorable. For example, you can find out how many apples have sugar content below 10%, or maybe how many apples have sugar content between 8% and 9%. So you simply count how many apples you have in your sample, which corresponds to this requirement or which corresponds to this requirement, and then you divide to the total number of apples that you have collected. That's how we compute relative frequency, right? Just an example. So here you can see that we have different outcomes of just rolling die experiment. And then, for example, we can compute the relative frequency of that we get an outcome which has 3 or less dots, right? So how many outcomes we have with 3 or less dots? So you can see this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So 6 out of all outcomes have 3 or less dots. And then the total number of outcomes, if you count all these outcomes, you can see 10. So it means that we rolled a die 10 times. And in 6 out of these 10 outcomes, we got 3 or less dots. So we can compute a relative frequency for this particular event having 3 or less dots, and that relative frequency will be 60%. Right? The question is, if we do it again, if we collect a new sample, what's the expectations from the outcomes? And in this case, because we are talking about theoretical expectations, we need to think of infinite number of outcomes. So if we roll a die infinite number of times, how often we will get 3 dots or less? And that's the relative frequency for the future event. If we repeat our experiment infinite number of times, that's exactly what we call a probability. So probability is expected frequency, expected theoretical frequency, if we repeat this event in future, if you repeat this experiment in future, infinite amount of times. So the sample size will be kind of infinite or very large number. So probability, it's number of favorable possible outcomes. So here you have observed outcomes, and here you have all possible outcomes divided to all possible outcomes. So here we have favorable possible outcomes, and here we have all possible outcomes, right? So again, if we roll a die, I don't know, billion times, how often we will observe 3 dots or less? That's what is a probability. Okay. So in this case, you know that if you roll a die and if every outcome is equally possible, then we will have 3 outcomes that have 3 or less dots, and 6 outcomes are possible in total. So the probability of having 3 dots or less, it's 50%. So the observed frequency was 60%, but the probability, the theoretical expected value, if we roll this die not 10 times, but 10 billion times, then it will be a 50%. So that's what probability is. That's the main difference between probability and frequency. Frequency is what we observe. Probability is what we expect in theory in future if we repeat this experiment infinite amount of times. Okay. So this is just to summarize. So when we talk about empirical data, experimental data, we calculate our experimental frequencies based on fixed number of trials. So the sample size is always fixed. We cannot run experiment infinite amount of times. And the way we measure different outcomes, we just simply compute relative frequency, how often we observe a particular outcome in our experiment, right? But when you think about probabilities, you need to think about future, you need to think about theoretical expectations with infinite amount of trials, and that's what we call a probability. So probability, it's how often you will see this particular event. For example, sugar content in apples less than 10%, right? If you analyze all possible apples in the population. Okay, so this is the theoretical expectations. And then an example with a coin. So if we toss a coin 10 times and got 4 heads, then we can compute a relative frequency of having head. So relative frequency of having head is 0.4 in our experiment. So this is 40% of the outcomes we got. But we can also say, if we toss a coin infinite number of times, and if coin is unbiased, so it's balanced, then in 50% of the outcomes we will have heads. So we can say that the probability of getting head is 0.5. So relative frequency is what we observe in particular experiment, and probability is what we expect to observe if we repeat this experiment large number of times, in ideally infinite number of times. Okay. Now let's talk a little bit about these probabilities. We will learn only what the minimum that is needed to understand the course. Well, first of all, probability, it's a chance that a particular event will happen. Probability always between 0 and 1. Probability of 0 means it's impossible to have this event happen. And probability equal to 1, it means it's always happened, so it's determined. Usually it's something in between, for example, 0.3, which means that if you repeat experiment infinite number of times, this particular event will occur in 30% of the cases. Or, in other way, you can also call it like this. If you repeat experiment only once, then the chance to observe this event is 0.3. So these are just two different definitions of the probability, right? And event can be anything. It can be, for example, win a lottery, or, for example, you got COVID, but without hospitalization, so you have a kind of mild COVID-19. Or maybe you run a water cleaning process, you want to invent a method that cleans water from pesticides, and then the event will be removing at least 50% of pesticides from water. So all these will be events. Now let's learn about two important properties of probabilities is when you have several events, how to deal with probabilities of several events. First of all, let me show you a very simple example. You can see that I have like 20 possible outcomes. Imagine that you have a box with different figures and then with different shapes, and then you just blindly take one shape. For example, it can be either a circle or triangle or square. So all possible shapes, you have 20 shapes in total. Okay. Now you can see that, for example, you have 10 circles. So it means that the chance to get a circle is 50% because it's 10 out of 20, right? It's the number of favorable outcomes. In this case, it's a circle. Divided to the all possible outcomes, in this case, it's any figure, so it's 20 outcomes, right? 10 out of 20, it's 50%. So this is the probability to get a circle. Now, the probability to get a triangle is 25%, right? So 0.25. So it means that in 25% of the outcomes, if you repeat this infinite amount of times, you will get a triangle because you have 5 triangles and number of outcomes is 20. It's exactly 1/4, right? So 25%. Now, what's the chance that you will get either circle or triangle? So what's the chance that one of these two probabilities will happen? Either you get a circle or you get a triangle. Well, in this case, you need to use the same idea. So you need to compute number of favorable outcomes and divide it to total number of outcomes. But in this case, any of these two outcomes will be favorable. So it means that you need to sum up the probabilities, right? Because you have 10 circles, you have 5 triangles. So it means that the chance that you will get one of these two, it's 15/20. Or you simply sum the probabilities up. So 0.50 and 0.25, it gives you 0.75, right? So this can be generalized as following. If you have two events, A and B, and these events are independent, so it's very important, right? So it means that probability to have event A doesn't depend on probability to have event B, and so on and so forth. And then the chance that either of these two events will happen, it's a sum of probabilities to get every event. For example, you roll a die, and what's the chance to get, let's say event A, it's when you get just one dot. Apparently you have 6 possible outcomes, they are all equally likely, so the chance that you will have event A, this is event A, it's 1/6, right? Then the event B is that you will get, for example, 3 dots. What's the chance that you will get the event B? Again, because all possibilities, all events are equally likely, it's also 1/6. But now you roll a die, what's the chance that you will get either this or this? Or this? What's the chance to get either of these two? Well, apparently you have 6 events possible, and then 2 out of the 6 will be your favorable events, so the probability will be 2/6 or 1/3, right? But on the other hand, you can also compute it like this. So possibility to have either A or B is probability to have A plus probability to have B, which is 1/6 plus 1/6, which gives you exactly the same, 1/3. So if you have two events that are independent, probability to get one of these two events, either, is a sum of these probabilities. Okay. Now let me show you another situation. Now imagine that we have the same configuration that we had before, but now shapes also have different line type. So some of the shapes have solid line, some of the shapes have dashed line. Now in this case I have 4 triangles. It means that the chance to get a triangle is 20%. It's 4 divided to 20, right? So it's a chance to get a triangle, it's 0.20. Chance to get a figure, any shape with dashed line, it's 50, 0.5, because it's exactly half of the shapes have dashed line and half of the shapes have solid line. Now, what's the chance to get a triangle which will consist of dashed lines? So what's the chance that I will have a triangle and at the same time this triangle will have a dashed line? So apparently in this case it will be 0.1. Why? Because that's exactly how many outcomes we have, how many triangles with dashed lines we have. We have only 2, and the total number of outcomes is 20, right? But you can compute it by simply multiplying these two probabilities. So the chance to get a triangle, it's simply a multiplication. To get dashed triangle, it's simply a multiplication of chance to get a triangle and chance to get a dashed line figure. So that leads us to a next important generalization. Again, if we have 2 events, if they are independent, the chance that both events will happen, it's a multiplication of probabilities for every event. Now, another example. Let's say you have 2 exams. Exam in statistics and exam in linear algebra. Let's say regardless how hard you work, the chance that you pass any exam is just a random chance. And then you know that your statistician, your teacher on statistics, just toss a coin, and then if it's a head, then you pass. If it's not head, then you don't pass, right? So if it's tail, you don't pass. So the chance that you will pass the statistical exam, it's 0.5. And then let's say that teacher for linear algebra does the same. So the chance that you will pass the linear algebra exam, it's also 0.5. So what's the chance that you will pass both? Well, in this case, according to the generalization we derived, it should be 0.5 times 0.5, which means 0.25. So it means that only 25% of students will pass both, right? How you can think about this? You can think about this as like a filter. So first, you have 100 students here, and because chance to pass the first exam, the statistics exam, is 50, you will have only 50 students who pass the exam, right, in theory. Now they will go to the second exam, to the linear algebra. But the chance also 0.5, but now it's 0.5 of 50. So it means you will have 25 students. So 25 out of 100, that gives you exactly the probability of 0.25. Okay. Now let's take another example. Let's say that you bought a lottery ticket and you know the chance of winning is 0.1. So every 1 out of 10 lottery tickets gives you a win, right? What if you buy 2 tickets? What's the chance that at least one will win? And what's the chance that both will win? Okay. Set this video on pause and then try to solve it and then come back for the solution. Okay, now the solution, right? So we have 2 events. So event A means that the first lottery ticket wins. So the chance for event A is 0.1. Event B, the second lottery ticket wins. The chance for this is 0.1. Apparently they're independent, right? So winning one doesn't influence on the chance for the winning the other one, right? Now let's think what you may have. You may have that none of these wins. So you have no. So this is A, this is B. No, no, right? You can have A wins and B doesn't. Then A doesn't win, but B wins. And then you can have also both wins, right? Now let's compute chances. What's the chance that none of these will win? Well, apparently the chance of winning is 0.1, chance of not winning is 0.9, right? And according to what we know before, we need to multiply these chances. So 0.9 times 0.9, which is equal to 0.81. So it means that this is the chance that none of the 2 will win. Now, what's the chance that this will win and this will not? Well, apparently it will be 0.1 times 0.9, right? And in this case, it gives you 0.09. What's the chance that this will not win and this will win? It's 0.9 times 0.1, which gives you 0.09 again. And then finally, what's the chance that both will win? It will be 0.1 times 0.1, which gives you 0.01. Now let's check that our calculations are correct. Well, first of all, these are all possible outcomes. So it means that if you sum up all these probabilities, you will get 1. And apparently you will, right? Because this gives you 0.9 and this gives you 0.1. So together, the sum of all these possible events, combination of events, is equal to 1. So that's correct. Now, let's try to answer the question. So what's the chance that at least one wins? Well, apparently, these 2 events correspond to at least one wins. So it means that you need to sum up these 2 probabilities. So the chance that at least one win, it's 0.09 plus 0.09, which gives you 0.18. So this is the chance that at least one wins. And then the chance that both wins, it's this one. It's 0.01. So this is the chance that at least one wins. This is the chance that both wins. And this is the chance that none of them will win. And then you can see that these 3 chances also sum up to 1. So you can see that in this example, we kind of apply both rules. We apply rules for multiplication of probabilities when we consider all possible outcomes. And then we apply rules of addition of the probabilities because both outcomes will be favorable to answer this question. So therefore, we simply need to add the probabilities.